Hi everyone. Welcome to our talk today. This talk is about the AI accelerator exploit, compromise the MTE enabled pixel from the DSP coprocessor. Hi, I'm Billy. I'm from Starlab. Do research on Linux and Android. Previous as a speaker of the HICON, ZhenPeng, of Taiwan and POC.
Hi everyone, I'm Peter from Star Labs. I do research on iOS and Android platform before. I have shared my past research on conferences like POC, ZeroCon, and OffensiveCon and other conferences.
Here is our talk agenda. First, we'll have some background introduction, then tell the bug we found, deliver the exploit, train with another vulnerability to get root from the show user, then MTE on the Android. Final do the conclusion. Since we do the research on the Android kernel, it has introduced many mitigation and security protection like PAN, PASN, UAO, CFI, PAC, MTE, and KSLR. Android enables some Linux kernel configure for security, such as init on seg and init on heap, bug list. Also, Samsung has its own mitigation, such as kernel, DFS, and physical ASLR. In Android, if a service does not exist on the target device, the exploit will not work. So we can classify the exploit by the attack service to the universal chipset, vendor, and the module exploit. Universal exploit uses a vulnerability they can attack almost on any Android phone. This is because the vulnerability is under the most core and foundational part of the Android ecosystem. For example, Linux kernel unit socket, TCP UDP socket, binder are the core IPC under the Android. When we talk about the chipset exploit, it means the attack service is from a certain chipset. For example, Mali GPU or Qualcomm GPU. It won't affect just a single module, but will impact all the devices use the GPU. Branch vendor might has its own driver. Exploit then will be the vendor exploit. For example, Samsung NPU, Samsung S-Clip GPU. The offense score will be very limited, usually only cover the branch module. Each mobile phone may have its own unique attack service, like Pixel GSP. Therefore, the attack service we are going to show today is under the module-specific exploit. Google Pixel has its own driver, such as Pixel HTPU, Pixel LWS, GSP, and Pixel Marine. So why we choose Pixel GSP? First, its attack service is new, introduced in 2022 with the Pixel 7. Not much information about the Pixel GSP, and no developer tool chain are public. There are also no relative CB in the past. Those reasons make us think it's good to try. When we look at the Pixel SE policy on a GSP device, we find out that untrusted app could perform I/O control system call on the GSP device. If we look carefully, we find that untrusted app content do not have the open permission. It can I/O control but can open. We think this some service help us to get the GSP device file descriptor. In the SE policy, HTTP app service appear to be the service. Untrusted app can get the GSP device file descriptor for this service. According to our reversing on the library lib HTTP client Google, function get DSP FD is the one that we can get a GSP device file descriptor for the COM Google HTTP app service. However, the HTTP app service won't pass the GSP device file descriptor if it is not in a long list. This service will check the caller's application signature only the signature from a long list can get a DSP device file descriptor. In other words, if we can execute within a long list application, we can access this attack service. Since no a long list app are all pre-installed, so this signature verification does not prevent us from install older and vulnerable a long list application. Now that we know we can access the DSP attack service, we need to know what DSP can do. DSP is used to replace the GPU in handle many common image process steps. It works closely with the edge TPU on the Pixel device. Also, Google Camera app can directly use the DSP. The following as-in policy tells that Google Camera app can access the DSP device. Google Edge TPU uses the same as-in policy as the DSP. The difference between the Edge TPU and the DSP is that Edge TPU has the vulnerability before, which is CB2023 35645. The CB2023 35645, this vulnerability is caused by the Edge TPU driver failed to lock MF read the inner function Edge TPU pin user page, result in a rest condition and cause the kernel memory corruption. However, we didn't find this kind of in the DSP, but there are many research on other different coprocessors: Marine GPU, Qualcomm GPU, Qualcomm DSP, and Pixel LWS, Samsung Exynos NPU, and Samsung Exynos GPU. So we wonder if there's a chance to get some idea from other different coprocessor type attack and try them on the DSP. Perhaps we can discover something. Vulnerability like write to the read-only file, such as CB2022 0847 is a dirty pipe. It's a good attack type on the Android. This type of vulnerability allows users to modify files. They are normally read-only and can cause local privilege escalation. This type of vulnerability also happens in a Marine GPU kernel driver. The problem is that the driver imports a page that originally read-only on the GPU, and then remapping into the CPU again, makes it as read and write. An attacker can then modify a file that was originally read-only and cause problem. Another type of vulnerability is page UEF and of the import GPU memory. This vulnerability often happens in the kernel driver of the Marine GPU. It allows users to exploit page UEF to achieve kernel rewrite. Another type of vulnerability is shrinker page UEF. Shrinker is used to reclaim the memory resource, release unused page to save the system memory. Often triggered when memory resource is under the high pressure. CB2024 32929 is a page UEF that happens when a shrinker page is used by the GPU and then freed by the shrinker. It allows users to exploit to achieve kernel rewrite. After we show some bug pattern, next I will hand to Peter for the root cause analysis.
Hi everyone. This part we will do the root cause analysis for the bug and share how we reproduce it on the device. We can see the vulnerability is located in the function GXP mapping create, which we can directly reach through the GXP map buffer IO control. Before entering the function, the code only performs some basic copying of user space parameters. First, we notice that a user-controlled dir parameter is passed in. The kernel then uses find extend VMA to retrieve the VMA corresponding to the imported user memory. And based on the VMA properties, it sets the FOL flags. I have pasted some code here. Initially, FOL flags is set to allow both read and write access. Even though FOL flags is well checked and updated according to the memory attributes passed from user space, but there's no synchronization between FOL flags and mapping point dir attributes. Instead, the mapping dir attributes is assigned directly from the user supplied dir parameter without any check. The mapping dir attribute is then used as a DMA direction when configuring the MMU on GXP side. This means we can continuously pass in the DMA bidirectional flag, causing the GXP to treat the system memory as read and write. In other words, even if we pass a memory region that is read-only on the CPU side, the MMU on GXP device will not enforce the read-only restriction. Instead, it will treat it as both readable and writable. This opens up a possibility of using GXP as a primitive to write read-only memory. I say possibly because so far this is a theoretical write to read-only primitive. We haven't yet figured out how to turn it into a working POC. Concretely, we don't know whether the GXP actually performed writes to that memory in practice. If the GXP firmware or driver never exposes an IO control or any operation that writes to that map region, this remains a theoretical issue rather than a real exploitable vulnerability. Before we start to write the proof of concept, let's take a step back. If we had a write to read-only primitive on GPU, how would we normally go about validating it? We can categorize validation techniques. One common approach is to perform the write from the CPU side to the memory region that was imported to the GPU as read-only. In our earlier example, imported GPU memory can be remapped in another CPU VMA. And the steps are, first, we import a CPU read-only region called CPU RO into GPU. Then we remap that same physical memory back to the CPU, but as a different VMA called CPU RW. Because of the get user page attribute bug, the remap VMA can end up with read-write permissions, and this mismatch would let us to write read-only memory directly from the CPU side. Another example is we create a CPU read-only region and then we import to GPU. After being imported, it marked read-write in the GPU's MMU because of the bug. In that case, we need to use GPU side write with either OpenCL or reverse engineered IO control. Before the Mali CSF feature, it was common to use publicly reverse engineered IO controls. For example, we can use the sum-in job IO control to issue the GPU write request. For GPU that has Mali CSF feature, the sum-in job IO control was removed. So people tend to use OpenCL instead. The practical reason is simple. There's been little public reverse engineering of the neural interface, so you cannot just borrow existing exploit workflow. So let's bring this back to our vulnerability. Although GXP supports importing a block of CPU memory, it does not remap that memory back to another CPU address space. Additionally, there's no public documentation, tooling, or an OpenCL stack for GXP that we could reuse. In short, we cannot fall back on the CPU remap technique or a ready-made GPU-side OpenCL workflow for a quick POC. Our first attempt was to emulate the GXP firmware. Even without OpenCL, we might be able to locate the coprocessor's firmware and run it under QEMU. By reverse engineering the firmware, we can identify the handler that performs write to the memory on the coprocessor side, and we trace the handler back up to the IO control layer, and then validate the behavior on the QEMU. If QEMU test succeeds, we can try the same steps on the real hardware. All right, let's work through the first step. In the GXP MCU firmware init function, its subroutine init MCU firmware buff copies the firmware into MCU firmware point image buff. Note that the image buff is not just a raw firmware blob, it's actually a structured object. So our next move is to dig into the initialization function to understand its layout and how the firmware is being stored. First, the initialization function locates the firmware resource from the device tree. The r.start field holds the firmware's physical start address. The code then calls device M memory map to map the physical region into the kernel virtual address. Once mapped, we can dump that memory to user space, for example, by writing a small kernel driver or using the BPF program, and then pull the dump off the phone for offline analysis. After loading the firmware into IDA, we confirm it's exactly what we need. The blob contains many strings related to DSPs, ring buffers, and mailbox. With that confirmation, we began firmware emulation and reverse engineering. After spending a few days on this approach, we realized that this path might not gonna work. First, QEMU does not support the firmware's hardware architecture. Many instructions don't behave according to the official menus. For example, the CPU-related registers accessed via the MSR and MRS instructions. We start patching them one by one, but eventually we realize there's just too many of them, and on top of that, the firmware has no symbols and making the reverse engineering extremely tedious. So, out of practicality and also with a bit of laziness, we decided to temporarily abandon this approach. Next, our second attempt was to replay attack. The basic idea was to hook applications that's using the GXP driver with some tooling and observe whether the target memory gets written. And if write occurs, we trace the full call flow and data flow. We will then replay the sequence to see whether it will achieve our goal. Okay, first we need to figure out which app actually used this driver. From earlier exploration, we already knew that apart from the whitelist apps like the YouTube family, the Google camera itself will use this driver. Since we want a commonly installed app, one that ships by default and is likely to invoke the driver frequently, we will pick this Google camera. And just a quick review of the SNX policy here, it confirms the Google camera app domain has permission to open the device and perform I/O control, read and write operations. By inspecting Google camera's memory mapping, we discovered an interesting shell library called libgxp.so. This appears to be the library that talks with the GXP driver, analogous to how libmali OpenCL.so interacts with the Mali driver. Within the libgxp.so, the function names give us a good idea of the library's functionality. For those who are familiar with OpenCL, the symbols like create device and create buffer options should look quite familiar. Back to the replay part. We use Frida for dynamic instrumentation and function tracing. Here, we hook Google Camera's I/O control function by getExportByName API. Using Frida gave us an overall function call logic and sequence, and thanks to the exploited function in libgxp.so, we didn't have to fully reverse engineer every I/O control and implement them by ourselves. Ultimately, we discovered that calling GXP copying open name library from buffer lets us to reach the problematic driver code. Finally, we are able to write a working POC now. By passing a read-only region into the GXP copy open name library from buffer function and using our hook I/O control to tweak certain parameters, we achieved the results shown in the screenshot. So to explain, we first create a block of read-only memory that initialized to 0, and after invoking the relevant GXP functions, the coprocessor will route AAAA to that memory, and with that, the validation process was complete. After we report the issue to Google, they refactored the entire GXP driver. The driver now obtains the GUP flag, which means get user page flag from the host address VMA. Then, the driver now derives GCIP map flags from the GUP flags. The GCIP map flags is adjusted according to the GUP flags and is then passed to the GCIP IOMMU domain map buffer SGT to perform the device-side MMU mapping. In short, the mapping flow is from the host address VMA to get user page flags, then to GCIP map flags, and then to GXP MMU. And that concludes the vulnerability overview. I will hand things over to Billy now to cover the exploitation details and the exploit chain.
Next, we will explain how we exploit this vulnerability to achieve local privilege escalation. The white read-only file, write-on-read-only file is already a very useful primitive. We try to use the same exploit path idea from the dirty pipe. Use write-on-read-only to modify the libc plus library, then hijack the init process by set property. So the init process, we use the write-on-read-only to write the kernel module payload in a certain location. Then we fork a child process from the init process. Switch to the asynchronous content to the more prop, and load the kernel module to disable asynchronous and get the root. However, we cannot reuse the write-on-read-only, so the init process to write the kernel module payload to the certain location. In the dirty pipe, it only requires a system call to trigger the vulnerability. However, from our exploit, we need init to open DSP device, but under the asynchronous policy, init process cannot execute IO control and open the DSP device. After search more on the asynchronous policy, we discover another possible exploit path. We can hijack Hell Camera default, which can perform the IO control and open on the DSP device. We also can map in the vendor file type to place the kernel module payload. Our goal now is to hijack the Android hardware camera provider to inject our kernel module payload again by the write-on-read-only. Unlike init, Android hardware camera provider cannot be triggered by the set property. However, we note that it will load the lib lock during the reboot. Maybe we can force it to restart and use the lib lock to hijacking. Force restart Android hardware camera provider, we encounter some challenge. If we exploit from the untrusted app, we cannot load the PID in the hijacking init process because of the high PID invisible. Camera provider PID is high, but init process can set the group ID to change the GID to the read prop, which is 3009, to get the PID. From the Linux kernel code, we can see if the GID is in a group, function has PID permission, will return to true. After force init to kill the camera provider, we can successfully hijacking the Android hardware camera provider to do the second stage attack. Our exploit process is as follows. First, we override lib, intending to FS with our own library. Then, we use the write-on-read-only attack to modify the libc and liblock in order to hijacking the init and camera provider. Next, we let the hijacking init to kill the camera provider PID, cause it to restart. During the restart, camera provider will load our control lib intending to have library. Next, the camera provider exploit the same write-on-read-only bug to write two payload. One is mod prop, which will launch a reverse shell, and other is lib S-node C2B list library, which will install a kernel module. Finally, init will execute mod prop, load our kernel module file in the kernel to disable asynchronous and return the raw shell. Since the whole exploit need take about 5 minutes to run, we just show the screenshot of the exploit here. He will return the raw shell from the pixel A once the exploit is finished. During the asynchronous policy, not while this application can access this driver, we find there is a property called vendor edge TPU service alone on this app. By set this property to 1, we can make untrusted app export this bar to root, but it's definitely not our final goal. We can check another bar to export this from low privilege. Now we will tell more about how we use another bar to do exploit. First idea comes from bring your own vulnerability application. Previously we mentioned that some non-default application can access the DSP driver such as YouTube Key and YouTube Music. One way to exploit is to find a vulnerable version of this wireless application to have code execution, then to train another train with our write-on-read-only exploit. Or we have another more general way. When we install a new Android application, PM% will try to find an available UID, and first available app ID was set to process first application UID as begin. When we remove a APK, and first available app ID will set to list app's UID plus 1 to prevent UID reuse attack. Also, the M first available app ID only will be increased to the bigger one. Within is also to prevent UID reuse. However, N first available app ID will reset to the process first app UID when system server crash and restart. So we know that as long as we can make the system server restart, we can become any application that we install. Combine it with the DSP bug, we are be able to reach the vulnerability from the shell user. Overview to the exploit chain. First, we install our app, then use run as to our application, and then uninstall attack application. Crash the system server to reset the UID, then install the wireless app such as YouTube Key. From now, the UID of the wireless application is under our control. And finally, use the DSP device to get the kernel code execution and the root shell. About this exploit chain patch, Google directly deleted the feature that allows third-party verification to use the DSP. Now I will hand to Peter to talk about MTE on Android.
Okay, and now we will talk about MTE on Android. So MTE refers to memory tagging extension. It's a mitigation introduced in newer ARM processors and is implemented in hardware. It helps to detect memory corruptions and use after-free bugs by tagging memory and pointers. And on Android, MTE first appeared on Pixel 8 as optimizing mechanism and is not enabled by default. Currently, it's only available on Pixel series after Pixel 8, like Pixel 8, 9, and 10. And it can be turned on with this device command, adb shell set prop ARM64 memtag boot control, and set both memtag user and memtag kernel. Since the introduction of MTE, many researchers have shared their insights, demos, and studies on it. Both the industry and academia have published articles and research papers covering various aspects of MTE. In short, MTE uses the high bits of the address to store tags, which are then used to check whether memory access are valid. For example, accessing memory beyond its allocation or accessing memory that has already been freed will trigger the MTE's mitigation. Essentially, it can be thought of a hardware-accelerated address sanitizer. From an implementation perspective, as long as sufficient compute resources are available, MTE are highly effective against memory corruption vulnerabilities. It could basically considered as a good game for such bugs. However, deploying it across all mainstream Android devices in the short term remains challenging. Apart from Google, manufacturers like Samsung, Xiaomi, Huawei, and Vivo Oppo, they are unlikely to enable it by default. And for now, none of them even has this feature. At most, it will be offered as an optional security feature, like iOS lockdown mode rather than a standard safeguard. So we know MTE is born for memory corruption bugs. And for logical vulnerabilities, MTE cannot prevent attacker to do privilege escalation. And MTE cost DOS sometimes might even help us to complete a chain. Next is our final section today, the conclusion part. First one is, for closed-sourced products and devices, record and replay attack is a quite efficient way. Next, for page-level memory corruptions and coprocessors or logical bugs, they are born to bypass MTE. And last one, logical bugs like write-read-only primitive will always win if there's no runtime signature check on Android phones. At the end, we want to share our timeline with the Android VRP. So we found this bug and write exploit at mid-2024. And we report the bug as well as the exploit to Google at September 2nd, 2024. And Google asked us for a non-precompiled lib at October 17th. And in case you don't know, Google only accepts source code in the reproduce steps. Any binary format payload is not allowed. So we sent back the new one 2 days later in October 19th. Then 3 weeks after, Google announced the bug bounty reward in November 9th. Since the severity is moderate at that time, and Google reward us $250. So 5 days later, we submit the exploit chain to Google on November 14th, 2024. And since that time, we keep mailing Google for half an year and try to convince Google that it's a high severity issue. And Google finally decided to reward bonus for the exploit chain, which is $32K, and admitted that even the bug itself should be high severity, not moderate. And at that time is May 29th, end of May. And then the CVE ID is CVE 2025-36905. It's assigned by Google. It's September 12th, 2025. And here's the references for our talk. So above is what we shared today. If you have any questions we have after the talk, you can always approach to us for any questions about the slide. And finally, thanks for listening.